Now that we've had a bit of basic review regarding parametric curves, we can begin to apply calculus to them. Specifically, we can find slopes, curve lengths, and also areas associated with parametrized curves. And so, considering our parametrized curves, which we generally define as x is a function of t and y also being a function of t, as long as they're differentiable at that point t, then we could say, well, x prime, or rather f prime of t, would be equal to dx dt, as well as y prime, or g prime of t, that would be dy dt. So we want to make sure we understand that notation. And considering this, dx dt and dy dt, they are related by the chain rule of differentiation. And so what that looks like, what we could say, dy dt equals dy dx times dx dt. And by balancing variables, we would see that those dx's cancel out, and this is a equivalent equation. And that can be rearranged. We could say, well, the derivative of y with respect to x, taking the parameter out and turning this into an equation with just x and y, would be defined as dy over dt divided by dx over dt. And again, you could see that those dt's would cancel when we consider those differentials as like a variable, dt over dt, those would go away. So this is also a true or balanced equation. And it works anytime as long as dx dt is not equal to 0. So the same type of rule applies to a second derivative, and d2y dx2. Well, that means you're taking the derivative with respect to x of y prime, which that will equal dy prime dt over dx dt. And so basically this says the second derivative is going to be the derivative of dy dt. So this is the second derivative of dy dt, and it's divided by the first derivative of x, dx dt. So that's how we'll find a second derivative. So let's, now that we understand what the first derivative and then our second derivative would look like, let's solve a problem. So for example, we're going to find the tangent to the curve using these two parametric equations, x equals secant t and y equals tangent t. Considering the parameter, t is between negative pi over 2 and positive pi over 2. We're going to find the tangent line at the point root 2, 1 when t is pi over 4. So the first thing we would start with would be finding both the derivative of x and y with respect to t. And dx dt, the derivative of secant, is secant times tangent. So we get secant t times tangent t. And the derivative of y, dy dt, is secant squared t. So that means, now that I know the derivative of each, derivative of y with respect to t, derivative of x with respect to t, the derivative of y with respect to x is going to be the ratio of those, which is secant squared t over secant t tangent t. And that simplifies by canceling a secant to secant t over tangent t. So that represents my first derivative, dy dx. And what we know about derivatives is that if I evaluate the derivative at the specified value, the derivative tells me the slope there. So if I want to find the slope when t equals pi over 4, well, what I would need to do would be to evaluate my derivative, dy dx, at t equals pi over 4. And what that would equal would be secant of pi over 4 over tangent of pi over 4. Secant is reciprocal to cosine. Cosine is root 2 over 2. So 1 over root 2 over 2 gives us root 2 for secant of pi over 4. And tangent at pi over 4, 45 degrees, is 1. So my derivative, root 2, what this represents is this is the slope of my tangent line at t equals pi over 4. So in this point, the point that we are considering, root 2, 1, was given. But we could easily, if that hadn't been given, I could have calculated that point by plugging in pi over 4 into t. That would give me my y value 1, and pi over 4 into secant would give me my x value, root 2. Okay, so we have an ordered pair, root 2, 1, and we have a slope. So if my point is root 2, comma 1, and my slope is root 2, then the equation of my tangent line, found by saying y minus y1 equals m times x minus x1, that would be y minus 1 equals my slope, root 2, times x minus root 2. And simplifying that, that is y minus 1 equals root 2x minus 2. Add the 1. We've got y equals the square root of 2x minus 1. And that represents the equation of my tangent line at the moment when t is at pi over 4. So let's do another example. So here we're going to find the second derivative of these two parametric equations. So x equals t minus t squared, and y is equal to t minus t cubed. So the first thing I'm going to do is I'm going to take the derivative of x with respect to t, and dx dt is 1 minus 2t. I'll also find the derivative of y, so dy dt equals 1 minus 3t squared. So that tells me my derivative, dy dx, is going to be 1 minus 3t squared divided by 1 minus 2t. So that represents my first derivative. So if I wanted, I could write that as y prime equals 1 minus 3t squared over 1 minus 2t. So in order to find the second derivative, I need to differentiate this with respect to t. So I'm going to differentiate this with respect to t, and then I'm going to need to divide by dx dt, my first derivative of x with respect to t. So let's look at how this works. My first derivative here, we need to use the quotient rule. So d dt of y prime equals 1 minus 2t bottom times the derivative of the top, negative 6t minus the top, 1 minus 3t squared times the derivative of the bottom, negative 2, all divided by that bottom or the denominator squared. And with a little bit of distribution magic, we get that d dt of y prime is 6t squared minus 6t plus 2 over 1 minus 2t squared. So I encourage you to make sure you can properly do the algebra there, FOIL, distribute, and get this new numerator. You might want to pause the video and do that. And what this represents is this is the derivative with respect to t of that first derivative. So the derivative of the derivative would essentially be the second derivative. But as we said in our previous slide, the definition here is going to be that d2y dx squared is going to be the derivative with respect to t of y prime divided by dx dt. So what that means is I'm going to take this piece and divide it by my first derivative of x with respect to t, this 1 minus 2t. So that's going to need to go in the bottom. So what we can say here for my second derivative, d2y dx squared, my second derivative of y with respect to x, is 6t squared minus 6t plus 2 over the quantity 1 minus 2t squared divided by dx dt, which is 1 minus 2t. And this simplifies. So my second derivative is 6t squared minus 6t plus 2, all divided by 1 minus 2t cubed. Because when I divided by that, it just took my denominator up a power. So this represents the second derivative of my parametric equations.